Hey everybody, Mr. Buck here with an example for your notes for today, where your target is that you want to be able to use proportions to find the lengths of sides of similar figures. And for those of you keeping score at home, this is section 510. First example we have here is, or definition I should say, is that similar figures are two or more figures with the same shape. So we need to know what similar figures are, and similar figures are two or more figures that have the same shape. So an example of that is what we have on the screen here. We have two figures which are triangles, and they are both right triangles, and they have the same shape. And they are both right triangles, so these are similar figures. Another way to say that is that we have two shapes that are, or two figures that are the same shape, and one's just larger than the other. It just has been enlarged by a certain factor, which we'll talk about here momentarily. So that's what similar figures are. The notation for this, in this case, is we have triangle ABC. This little squiggle line means similar. So triangle ABC is similar to triangle XYZ. So these two triangles are similar. And we can say that. We can say that we're trying to make them be similar or make them look similar by using this notation. So even though some might say that these two triangles do not look similar, they indeed are because of the notation saying that they are similar. And the orders of the vertices matter. So we say ABC and then we say XYZ, and we say that on purpose. We can't just say ABC and then XZY, because A corresponds to X. If I look at this corner here, A, this corner or vertex here corresponds to this vertex. It's in the same spot. So if I took this triangle right here and I made it bigger, vertex X would line up with vertex A. And this might be easier to see with vertex B, because vertex B is the 90-degree angle. What corresponds with that? Y in the lower one, because the Y has the 90-degree angle also. So B corresponds to Y, and that is seen in the similarity statement here. And then lastly, Z corresponds to Z. If we enlarge this triangle here, Z would line up with C. So those two things are what we call corresponding. They're in the same position of two different or similar figures. There's a couple properties about similar figures. The first one is that corresponding angles are equal, and that's kind of evident here with angle B. Angle B is 90 degrees, and also angle Y is 90 degrees. These two angles are corresponding, and their angles will be equal. So if we knew the measure of angle X, we would also know the measure of angle A. So we know that B is 90 degrees, so therefore Y is 90 degrees. If I tell you that angle C here is 30 degrees, we know that Z is also 30 degrees because these two angles are corresponding. And lastly, if we say that angle A is 60 degrees, we know that angle X is 60 degrees also, because they are corresponding angles from similar figures. And we know they're similar figures because we are told that they are similar figures. So in similar figures, corresponding angles are equal. They're all the same. The next thing that's true is that the ratios of the lengths of the corresponding sides are equal. So a couple things we got to think about there. This is also called the ratio of similitude. So this example means that if we say that this side right here, AC, that the hypotenuse of this right triangle is 10 centimeters, and then we come down and we say that the hypotenuse of XZ is 5 centimeters, the relationship between these two will be the same relationship between all of the other corresponding sides. So what does that mean? Suppose we say that this side length right here, BC, is 8 centimeters. Well, 10 to 5, that relationship is divided by 2. So if we want to get from 8 centimeters to some mystery number, this side length here, we would do the same thing we did to the 10 to get to the 5. Divide by 2, so we're going to take the 8 centimeters, divided by 2, and we'll find that this down here, it says 4 centimeters. I don't believe you can see that on the screen there, so apologize for that. But this, what it says is this side length right here is 4 centimeters. You can see the little tip of it there. And I can't move that up, so I'm sorry. But this side length right here is 4 centimeters, because that's the same relationship as 10 to 5. The relationship of 10 to 5 is the same as 8 to 4. The last one we will be able to see if we say that this side right here, AB, is 6 centimeters. The corresponding side, which is this right here, is going to be 3 centimeters. because 10 to 5 is the same as 6 to 3. So if we were to kind of line this up as a ratio, say the large side length to the small side length, we would have 10 to 5, 8 to 4, 6 to 3. The difference between these fractions or these ratios is nothing because they all reduce to 2 over 1. So we would say that the ratio of similitude is 2 over 1. 2 units on the large triangle is 1 unit on the small triangle. And we can see that with the ratios of the large to the small that are provided in the given triangles here. And we can also flip that around. We can say, well, we don't want to go from the large to the small. What if we want to go from the small to the large? So we would just take the reciprocal of all these things. 5 to 10 is the same as 4 to 8 is the same as 3 to 6. So if we were going from large to small, then that would be a ratio of 1 over 2 or 1/2 or 1 to 2, however you want to say that. So these two things, while these two ratios are the same, it just depends upon which triangle are you working from first. Are you doing a ratio of the large to small, or are you doing a ratio from the small to large? And it really doesn't matter which order you go in. Those two ratios will end up being the same all across as long as you're doing small to large the whole way across the top and the bottom.